Let's move to special types of events and how their probabilities interact. In this section, we'll explore 5 key types, and they are intersection events, union events, complementary events, independent events, and dependent events. Each of these gives us a deeper insight into how events can combine or influence one another. An intersection event occurs when two events A and B happen together. So we have event A and we also have event B. So this is the intersection part here. So this shaded region in the middle represents the outcomes common to both events. And this is denoted by this or this. For example, if event A is students who play football and event B is students who play hockey, then A intersect with B represents students who play both sports. The probability of this intersection measures the likelihood that both events occur at the same time, which can be found by using this formula. The union of events refers to the occurrence of either one event or both. So here we have two overlapping events here of event A and B. This union expands our scope. Instead of focusing on overlap, we count all outcomes that belong to either event. This is denoted by this, meaning A or B or both occur. The formula that connects union and intersection is given here. That subtraction avoids double counting the overlap between A and B. A complementary event shows what happens when the event we are tracking does not occur. So if we look at the sample space again, so let's say we have event A, the complement will be the area outside the circle. So if we call our event A, then its complement is written as A prime. The probability of A prime is simply 1 minus the probability of event A. So if there is a 35% chance that event A will happen, there is a 65% chance that it won't happen. This concept is especially useful in real-life contexts like reliable testing, where we might measure the chance of system failure as a complement of the chance of success. Three events are independent if the occurrence of one does not affect the occurrence of the other. For example, when flipping a coin and rolling a die, the outcome of the coin toss does not affect the die result. So mathematically, independence can be defined as this or this. This can also be represented by Venn diagram when there are two separate circles here. This formula means that if A and B are truly independent, the joint probability equals the product of the individual probabilities. However, many real-life events are not independent. One can affect the other. Let's explore those. Events are dependent when the outcome of one affects the likelihood of the other. For example, drawing two cards without replacement from a deck, where the second draw depends on the first. Also, when we select two balls from a bag without putting the first back, again the second draw's probability changes. In such cases, the probability of both events occurring is this. Or it can also be found by using this formula. where this probability means the probability of B given that A has already occurred. Let's look at a few examples. Here are some examples of dependent events. We draw a card from a deck, not replacing it, and then drawing a second card. We select a ball from an urn, not replacing it, and then selecting a second ball. Next, we have having high grades and getting a scholarship. And also, we have parking in a no parking zone and getting a parking ticket. These examples show that probability isn't just about numbers, it's about understanding relationship between events. Dependent and independent events form the core of how we model cause and effect in probability. Now that we understand how events can relate to or influence one another, we are ready to explore how probabilities combine, beginning with joint and marginal probabilities in the next section.